One of the keys to designing an energy-efficient home really starts with having an understanding of heat transfer. First of all, heat always goes from warmer areas to colder areas. In the winter months, the heat inside our home wants to naturally go to the colder outdoors. In the summer months, the warmer outdoor air naturally wants to move to the cooler indoors because we air condition. Another factor is that the greater the temperature difference, the faster heat flows. Heat basically is transferred in three basic mechanisms. The first one is conduction. That's basically when you touch something and it feels warm, that's conducting that heat from that object to your hand, for example. The second mechanism heat transfer is heat transfer by convection. Convection can be likened to when air infiltrates into your home, it pushes out the air that you paid to heat and cool. And warmer air, since it's more buoyant than cold air, has a tendency to rise, and we call that the stack effect. Another factor of heat transfer is called radiation. Radiation heat transfer happens like your warmer body wants to radiate heat to a colder surface. Or for example, if you're staying in the shade and you step into the sun, you immediately feel that radiant energy from the sun. Now we use low emissivity glass that's basically heat reflective to reject or reflect some of that heat from the sun. Or we use radiant barriers in our roofs so that the heat energy from the sun does not get re-radiated into the building envelope. That's how we control heat transfer by radiation. We control heat transfer by convection by using air infiltration barriers or air barriers around the outside of our house because that stops the air from infiltrating in. And then thirdly, we use insulation to help stop heat transfer by conduction. So let's go inside and take a look at some insulation. What gives insulation good insulation properties is its ability to trap air. We measure insulation by R value. The greater the R value, the greater the resistance is to heat transfer. When we have lots of air pockets, that creates a resistance to heat transfer that increases the energy performance of our homes. Now, a typical insulation that we use in homes is, for example, fiberglass is one of the most common ones. This, for example, here is a friction fit bat. A typical stud bay, for example, is 14.5 inches wide. Well, this fiberglass bat would be about 14 5/8, just slightly wider, so it is held in place by friction. Another type of bat is what we would call a craft-backed insulation. This is where we have a asphalt-coated paper, which acts as a vapor retarder, which is required by some building codes. The thicknesses of insulation that we have for 2x4 walls are basically 3.5 and 3 5/8. Now the R values varied based on the density or the amount of fiberglass that's in the bat. So for example, for 2x4 walls, we have R11 bats, we have R13 bats, and we have what we call a high density R15 bat. In 2x6 walls, we have R19 bats, and we have R21 bats. Now what's interesting about the R19 bat, it's actually 6 1/4 inches deep, but a 2x6 stud is only 5.5 inches. So really, when you take a 6 1/4 inch bat and you compress it to 5.5 inches, you really only get an R17. Now, other ways that we can insulate walls are with foam insulation. We have two basic types of foam that are spray-on. We have an Icynene type product, which is an open cell insulation, and its R value is about 3.5 per inch. We have closed cell polyurethane foam, which has an R value of 6 to 7 per inch. Other ways that we can insulate cavities is with spray on fiberglass, which can be wet spray, or wet spray cellulose. And basically what we do here is that we take a binder and a liquid, say starch and water, and we mix that with chopped up, ground up newspaper basically, and that's cellulose, and then they spray it on the wall. And again, they have spray on fiberglass and spray on cellulose. They also have blown-in insulation that where you net the walls and you basically would blow in fiberglass into the netted area. Now we also use on the outside of buildings for sheathing, we have what we call insulating sheathing, and there's a couple different products that we use for that. Most common is extruded polystyrene, what we would call in the trade name would be styrofoam, and it has an R value of about 5 per inch. Another type of foam insulation that would be rigid would be expanded polystyrene. Now that's not nearly as dense, doesn't have nearly as many air pockets, so it's not quite as good an insulator. In fact, it has an R value of about 3.5 per inch. And then another type of foam is polyisoensanurate. It probably has the highest R value, and it has an R value of about 6 to 7 per inch for a rigid foam sheathing. Now in attics and ceilings, typically attics will either use bat insulation or we'll use blown-in insulation, which could be either cellulose or blown-in fiberglass. We can also use spray foam insulation. Typically we'd like to use closed cell for attics wherever we have an unvented attic and the insulation is sprayed to the bottom of the roof deck. Now, insulation that we use in basements oftentimes is going to be a rigid polystyrene that's glued to the walls, and that works fairly well for basements because you don't have to worry about summertime condensation on a cold basement wall like you would with frame materials and fiberglass. They also have insulation materials that they put on the outside of basements. One product, for example, is Tough and Dry, which is a rigid fiberglass insulation. They also put rigid polystyrene insulation on the outside of basement walls as well. For crawl spaces, oftentimes they will either insulate the floors with fiberglass or they'll insulate the perimeter of the crawl space with a rigid foam type insulation. Typically they'll insulate those to R10. Common insulation values for walls range from R15 to R19. For attics, we typically see attics insulated anywhere between R30 and R38, and floors typically anywhere from R10 to R19. Another component to the insulation system or to a building envelope are vapor retarders. Many codes require vapor retarders, and a vapor retarder is basically a product that has a perm rating of 1 perm or less. What that basically means is, in terms of permeability, it's the ability of a material to allow moisture vapor to pass through it. And the concept is that in cold climates where we have a lot of humid air inside the home, naturally that heated air wants to try to find its way to the colder outdoors because heat always goes from warmer areas to colder areas. But the concept behind a vapor retarder is to keep that moisture vapor inside the conditioned space so it doesn't get into the wall where it could potentially condense. Now moisture vapor moves in and out of houses in two ways. One, on air currents. In other words, air contains moisture, and when that moisture moves from one location to another, it carries that air with it. That's why it's important that we foam and seal around all the penetrations, and why we use building wraps, for example, on the outside to stop that airflow. The second way that moisture vapor moves is by diffusion. That's the process of a material absorbing moisture and then drying to a drier environment. And of course, vapor retarders are designed to prevent that. Polyethylene vapor retarders, however, in some climates where we have cooling in the summer, can actually create a problem because moisture vapor from the outside that gets in the wall cavity can condense on the back of the poly and cause lots of problems. Now, what determines the level of insulations that we have in homes are basically climate zones. In the United States, we have 7 climate zones, 1 through 7, and the warmest climate would be climate 1, and the coldest climate would be climate zone 7. The whole process of really designing a good building enclosure or an energy-efficient building envelope is to really create homes that are comfortable, durable, and energy efficient.